There we go. So we ended on slide 15. So this is slide 16. All right. So the ship, since we were talking about shipboard applications, has two different DC 24-volt systems. All right, let me just see if this is someone emailing me. Okay. All right. So normal operations, like we talked about, normal full operations where we have shipboard power is going to be charging the batteries. All right. So we're sending electric current to both of these battery banks. And then also we're sending it out to the general alarm. All right. And also our internal communication circuit. This is normal operations. All right. So if we lose power, we lose the plant, we'll have a battery backup until our DC, or basically our emergency generator comes back online. So this is all emergency power that comes off of these batteries. Now, that is the end of DC lines that we're going to talk about, DC circuits, at least for a little bit. Let's move into alternating current, all right? Otherwise known as AC systems. Now, alternating current is basically, it alternates, all right? So it's going to be in a wave pattern, and it's basically just going to flip back and forth. It's just constantly moving the electrons almost like this. You're not having a constant flow where one electron is moving all through the pipes, all the way through and all the way to the end. It's almost reciprocating the electrons back and forth and charging them to go back and forth. All right. AC current reverses direction according to this pattern. The big thing that you'll see is that light bulbs all around us are actually flickering, but they're flickering so quickly that we won't actually be able to see them. All right, that's even happening right now. So let's just talk about a quick couple definitions. I know a lot of you have probably seen this just in physics in high school, and then also you'll learn more about it in the physics that we have for engineering right now. So what we have is magnitude. That's our peak value. That's the top part of our sine waves. All right. And then we have our effective value. And this is where we're going to actually be taking our 120 volts. So this is like our 120 volt line. Okay. And notice the big thing that we're going to talk about is this goes above those lines. Go back a little bit. That was a little too quick. So going on from there, we have our frequency. Our frequency is the time period in seconds between one full cycle. All right, so it's the time between the peaks for one cycle of here. This is one full cycle until it comes back to the same point. All right, it's the number of cycles completed in 1 second. So frequency is 1 over T in hertz. All right, in the US, the standard frequency is 60 hertz. Now, I'm going to have a video posted up to Blackboard. It's this Brit who's talking about electricity. He does a very good job of talking about 3-wire, as we'll get into later on. And he shows it to a point where I won't be able to show it to in my own home. But he talks about having 50 hertz. All right. And he also talks about that it's not 120 volt system. It's like 110. All right. So it's 50 volts, 110. And that is where you'll end up in different countries. Different countries have different standards. We in America have, in the US, we have a 60 hertz, 120 volt standard. All right. That's what all of our electrical components, all of our computers, our tablets, everything is going to be based off of these two numbers. All right. How they charge, what is the voltage ratio coming in and out of certain electronics. And this is why if you were ever to bring, like, say, a laptop over to Europe for a little while, you would have like a lower charge rate. You wouldn't be able to handle charging your laptop constantly to this level. This is a different electrical charge, and it will slowly deteriorate the battery. It's not going to explode. It's not going to have any sort of real damage. It's not going to catch fire, but long-term damage will be, maybe instead of having a 4-hour battery life, you might have like a 3 hours and 15 minutes. After like 4 years of charging it. It's just very slow, but it does do some damage. All right. And this is why you have locked electronics. Certain electronics won't work in certain countries. So, continuing on, we have basically our phase. All right. Being in and out of phase. We have our 0 point is right here. This is T0. All right, it's the starting point. A voltage or a current with a 0-degree phase angle starts at the peak value. All right. Then we have a positive phase angle. This is if we were to have something that would look like this. All right. And then we have a negative, and that's the same thing. It would be something that would be over here. And I'm crudely drawing this. But still, this would be our positive, and this would be our negative. And that's our phase angle. So let's get into actual electricity. So this is a single phase, 2-wire system. And a single phase, if anybody's been in an older home, you have basically outlets that look like this. All right. And the big thing is we should notice like this is there's no like third eye. There's nothing here. All right. So this is not 2-wire. It's not a 2-wire system. This is a very basic way of doing electricity. We won't be doing basically nothing is built this way, and we'll talk about those reasons a little bit later in the lecture. But just know that this is single phase 2-wire, where one is the live and the other is the neutral. All right. So we have our ground, our neutral wire. All right. It's a ground potential. It has 0 volts. All right. We have our effective value of 120 volts. And the big thing we should notice is that our sine wave is going above and below our effective value. All right. Oops. Now, we do have a new symbol that has shown up. It's the symbol right here. All right. That is a ground symbol. They will come off of a wire in a wiring diagram, and it basically just means that it's connected to ground. All right. And this ground right here, if I have 2 wires in the system and one has a ground symbol coming off of it, it means that this ground, this wire A, this wire A is connected to ground. And wire B is not. All right. But if I add a ground to it over here, having 2 wires that have grounds to it, it means that it's connected together. It's almost like having 2 wires that would just be like that. All right. Those grounds are connected. All right. So that's the new symbol that we have. That is the ground symbol. So single phase 3-wire AC. So we have a live wire A, we have a ground, and then we have a live wire B. We still have our ground, which is our neutral, 0 volts. So live terminal A rises above and falls below the ground potential. And they have live terminal B falls below and rises above the ground potential. Both live wires are at 120 volts. So if we take their effective value in between the two, we get 240 volts. Now let's talk about 3-phase 4-wire systems. So we still have our ground, our neutral. We have our phase line right here. All right, so this is going to be phase. We have our live wire A. Then we have a live wire B. And then we're going to have a live wire C. And now each one of these wires and each one of these electrical signals are 120 degrees out of phase with each other. So from the ground to neutral, we're going to have 120 volts. That goes to each one. And they're all, like I said, 120 degrees out of phase. So our phase voltages are AN, voltage BN, and voltage CN. But now we have also B to A, C to B, and A to C. Each one of those are our line voltages. So A to B, B to C, and then C to A. So 3-phase 4-wire. Basically, here's just some quick math to explain it some more. All right, so we have our maritime college, we have our industry facilities, and we have Con Ed distribution. All right, so we have our line. So our dual voltage, and then our line voltage. So 120 volt between A to N, 270 from A to N, 2400 from A to N. All right, so 2400 times radical 3 is 4160. All right, so from A to C is 4160 volts coming out of Con Ed's distribution. Now, this will make more sense as we use an actual diagram. So we have a 4-wire, 3-phase, 4160 voltage utility line. All right, the topmost line is our ground, and then we have 3 wires that are live. We have a transformer. It's a 10-to-1 step-down transformer. And we connect one of the 3 wires that are live to the top of the transformer. And we have our ground attached to the bottom half of the transformer. And then coming off of our transformer, we have another ground, and the grounds are going to be connected. All right, so you are going to have a continuous ground all the way from your house connected to the power plant. So these transformers are taking 4,160 volts, and they're stepping it down to 120 volts, all right, but only on 2 lines. It's not a 3-line system coming in, all right? Now, this gray piece from here to here is just the conduit. All right, it's just a pipe that holds 3 wires or 4 wires or 1 wire. It's just a piece of pipe. All right, you still have all the wires inside of it. Whoa, how did I get to this? Now, one transformer will basically take care of about 4 or 5 houses. All right. And the big thing is that we're going to learn about in a second is what happens after we get to these meters. All right. So we have wires that are coming in at 120 volts. 3 of them, 1 of them is ground, 2 of them are live. So here's our meter. This is what's going to be calculating how much electricity we use in kilowatt hours. And our 3 wires are coming in. This is our circuit breaker panel, and we have a new symbol. All right, these symbols right here are breakers. All right, they usually don't have to have this little box. Most of the time, you won't see them with a little box. All right, you usually will just see them with a half moon with 2 wires disconnected. All right, and all it's representing is a circuit breaker. All right, so that's another new symbol that we've learned. So if we want to have any electricity that goes to our house, we have to have a branch come off of it. Each branch will have their own circuit breaker, but it will only be on the live wire. Notice it's the same here. We have 2 circuit breakers, but they're only on the live wire. The middle wire is ground. All right, so we are taking power from one 120 volt live wire, and we're taking a neutral to our neutral. All right, so this is still the same ground. It's still attached to that light pole. It's still attached all the way back to the power plant. But as we go through, each room will have its own power that comes off of the 120 volt circuit. Whoa, I just gave an answer away. So going through this, each one of these is 120 volts. Our blue and our reds are 120. How are we going to get 240 for our laundry room or for our fridge if we have an industrial fridge in our house? How do we get 240 volts from 140 systems, 120 volt systems? Because electric dryers will need 240 volts.
Three-phase system?
A 3-phase system? It's not necessarily going to be a 3-phase system, but you're on thinking the right path. All right. Remember, we have, here we go, found the pen. So right now we have 2 wires coming into the house at 120 volts, but we want to get to 240. How can we get more power out of 2 wires? What would we have to do? How would we connect it in the circuit breaker? Who has like a propane dryer at home? Who has a gas powered dryer? Does a lot of people have an electric one?
Yep.
All right, so what's the main thing is when you see those electric ones? What do they look like when you see the outlet for it? How does the outlet look? Does it look like this, where it has basically two eyes and then a neutral here? What does it look like? For the outlet for your dryer.
It's like a massive socket.
It's a massive socket, so it's handling a lot more electricity. It's a 240 volt. All right, so after today's lesson, just kind of go take a look at it, but they pretty much look like this. All right. Somewhere along those lines. Now, they're done because, one, you don't want to stick 120 volts a light bulb or whatever into a 240 circuit. All right. It's to protect idiots, which when you do engineering, you figure out that's about half your job. All right. And number two, it's done that way to handle the higher voltage. And the way we gain that higher voltage is through two circuit breakers. All right. So what we're looking at here is instead of having one live wire, we are having two live wires coming into our 240 volt. So we have two 120s adding up to 240. Okay. And that's why you see, if you pop open your circuit breaker panel, you'll see two circuit breakers with a bar across them, connecting both of them. And that is a 240 volt circuit breaker. All right, because it has two live wires coming out and going together in conjunction. So let's talk about that little nose there, that third wire. So basically, we have a ground and we have circuit breakers to protect our equipment and people. All right, so if it senses a huge amount of current coming through, all right, they have a popping level, just like a safety valve that we have. It has a set point. If too much current goes through the circuit breaker too quickly, it will pop and it will open up this right here. It will pop open like a switch, all right, and it will stop the flow of electricity. So once it trips, it pops open, and now you have no electricity flowing because this is the only way you are going to get voltage coming into that system. All right, so that's a circuit breaker. So this is why I'm saying, and I was talking about earlier in class, you're never going to find a two probe circuit anymore. All right, this is built with a 3-prong face because it's there to protect you, the person, the operator. It's done at home, it's done everywhere. And the idea is that right here, this is a toaster and you have an electric wire, all right, and right at that toaster, you have, all right, that squiggle line in the middle is the wire, and then these two horizontal are basically your insulation. All right. So if it's exposed, you can have a flow of electricity escaping. All right. And knowing about electricity, it always wants to find the quickest way to ground. So right here, you could just be unlucky and it'll fray right there. And now you have exposed wire. So this electric toaster that is all metal and not plastic is a very good conductor of electricity. But these feet may be rubbered to, protect the tabletop or plastic. Or even if it's old and you did get a metal one, think about what's going through in your house. This might be made of granite. This might be made of a concrete. This might be made of all sorts of things. But even if it was made of metal, if you had a stainless steel countertop, it's still connected to wood. Wood isn't a very good conductor. All right. Now, going through all that, think about how many layers that electricity would have to go through. If you grab this toaster and this toaster was plugged in, you have electric current coming out of this live wire. And now this whole toaster is electrified. It's just sitting there waiting for you to pick it up. It wants you to pick it up. You're going to get electrocuted because your body is a very good conductor. and it wants to flow from high to low. All right, so it's going to flow through your body and out your foot and go to ground. That's its main deal. It always wants to go from high to low. So this center eye, this grounding wire that everyone talks about, is there to protect you in case you have any sort of anything that happens on this wire. All right. So in order to protect you, they have these ground wires. It's connected to the ground in the circuit breaker. And if you notice, if you pull open a 3-wire, you have 3 wires. You have a ground, you have a live, and you have a neutral. All right. The ground is attached to here. You have the live wire and you have the neutral wire. The ground eye isn't attached to the circuit. If you notice, you have a heater coil that's right here. It's not a part of the circuit. It's not supposed to be where electricity is flowing. All right. But where it is attached is to the physical toaster. All right, so if this fails right here, and we have a failure point again, you will have electricity to flow out of the toaster and through this ground strap to the ground. Because that's the easiest way for it to flow. And it basically, if you pick this up with your hand, you might get a little shock, but more than likely, it's just going to be really, really hot. All right. It's there to protect you and you alone, and also the equipment. You don't want to have electricity flowing through pieces of equipment where all of a sudden, if you have a 120 volt circuit over here with a step down transformer, with a 12 volt circuit over here. And if you have a frayed wire on this 120 volt line, you don't want someone who's picking up or prodding on the 12 volt line, on the 12 volt side. They don't want electric current to go through the 12 volt side and destroy the equipment. They want it to come back and go through the ground. So it's there to protect the equipment too. So if you go pick that up, it's still connected and you won't get electrocuted. All right, you'll probably just be wondering why you still have bread and not toast. So enough with residential. Let's begin our talk about going into shipboard. And ships do not have a ground. Electricity on ships don't have a ground to them. They aren't connected back to any power plants. Otherwise, ships wouldn't really get very far because they would be tethered back to shore. All right, so instead of having a ground here, and if you notice, we just lost this piece. So now we don't have 120 volts going here. All right, there's nothing from a neutral to here to create 120 volts. All we have is line voltages. So we have 450, 3-phase, 3-wire, ungrounded. All ships ungrounded. So we have our A, B, and C wires. All of them are live. So where do we get our 120 volt for lighting? And the answer to that is transformers, because we are doing Jeopardy. Answers first, then questions. All right, so 450 volts come in to a transformer. But unlike what we were talking about residential, this side of the transformer is not attached to ground. It's attached to another live wire. All right, and what comes out on the other side is 120 volts. And again, the big thing that we should see here is that this transformer right here is an A to B transformer. I shouldn't do it that way. A to B. And then right here, we have a B to C. And then this one right here, we have a C to A. All right. Now watch this as it goes through. This color sequence. It's very specifically done. It's creating a potential difference between the two. From A to B, A is lit, B is black or blue. All right. And then B is lit and C is blue. And what's happening is that are all 120 degrees out of phase with each other. And so your potential difference, because it's AC voltage, if this was DC, this would never work. Because it's AC voltage, we have a potential on A and a 0 volt situation here. So you have travel. All right. And that's how we're getting 120 volts coming out of this side. And then those go off to our lighting panel, and then they can go off to do different things as well, but this is what we're just going to go into our lighting panel. They have a 3-pole circuit breaker. All right. If they are boxed in together like this, it usually means that they are connected. So they would have a line that would go across them. So ungrounded lines. Same sort of circuit panel that we would know and love. All right. But the big difference that we're seeing is that every single line has their own circuit breaker. All right. Because technically both lines are live. So they're 1-phase, 3-wire branches. And the big thing we should take away is that AB, AB, even though they're going to two different locations, we have AB is stateroom port inboard forward. And then we have stateroom starboard inboard forward are both using off of the AB line circuit. Same with AB down here. Our staterooms port inboard and staterooms starboard inboard aft are still using that AB line circuit, but they are on different circuit breakers. So let's talk about grounding and what happens when we ground. Now, there is a really good video on YouTube that I'm going to post after this class. All right. It's from the MEBA school. He goes through into depth on this about grounding lights. All right. And he really physically shows them better than what this animation can. And as we go through with this, you guys will see it. But please watch that video. It does a very good job of it. He talks about Y and deltas formations of wiring. Just know for this point in time, that's different ways that you can wire these 3 wires. All right. But what I want you to pay attention to in his video is the ground lights. All right. So let's talk about grounding. Now, like I said, there is no ground on a ship except for this one location. And this one location is physically tapped into the ship. All right. And that ground is right here. So when you guys were in the engine room and you saw both TGs, both turbo generators for electricity, there was our main lighting panel. And on that main lighting panel, we have 3 light bulbs. Like we have 1 here, 2, and 3. All right, so 3 light bulbs and a push button. All right, those are our ground indication lamps. And they're going to let us know is that if any wire, A, B, or C, get a ground in the system. So right now we have a ground coming off of A. This isn't a good ground. This is like a motor grounding itself, or a toaster. Any sort of equipment, or even just the wire scuffed up in the wall, It's grounded. It's grounded to the ship. Now, if we look, this wire comes off, and it goes from here through a circuit breaker and into our load. Now, we also have our ground indicating lamps. And if we look, we have 450 volts between A to C, B to A, and C to B. All right. Now, all three of them are connected right here in this pattern. This is called a wire connection, W-Y-E. All right. Now, they're connected and they're grounded to each other. So, and they're also attached to this ground here. When there is no ground on the system, all three bulbs will be lit in the same intensity and they'll be lit together, all right? But as soon as you have a ground like we have here, one bulb will go out. And what is physically happening is, like we said in the beginning of this class, this ground here is attached to this ground. You might as well have a wire connecting both of those. So what is happening is that you have 450 volts coming in on both directions here, and you have 450 volts coming here. But the big difference is that these are in the same phase, so they cancel each other out. This light bulb will never light because they are canceling each other. Whereas these sides are out of phase of each other, and they're creating a bigger potential difference, so they're going to light brighter. And since they light brighter, because of this, because they're getting backfed with 450 volts on this side and 450 volts on this side. So that is physically why this light will detect the ground. All right. Now we have a push button right here, and this push button is a new switch that we haven't seen before. All right. And it really does show like a push button. And the push button itself is basically like a finger would go here. All right. And you would push downwards on that push button, and you have a wire here and a wire on this side. So what normally open or normally closed would this push button be? Would it normally open or normally closed? Was an answer for me.
Normally closed?
Yeah. Why would it be normally closed?
Because he's already pushing down, which is making it open.
Exactly. So there would be like a little spring right here. All right. And that's exactly right. So this would be a normally closed N-O-R-O-M-A-L-E-Y. Remember, if you write messy enough, no one can tell that you're a bad speller. So there's a little spring right here, and this is a normally closed button, which means when it's unpushed, it's connecting this side to a ground, and the only ground on the vessel. But as soon as you push down on it, you're opening up the ground. So if you're in this scenario right now, what's going on? You are, like I said, this ground right here might as well be connected as a wire. So instead of having two sides here of voltage being fed on the same phase, what is going to happen as soon as you push down on this button?
You only have one side.
Exactly. So what happens after you only have one side on this specific light bulb? Well, actually all three. What would happen?
They all go back on?
They would all go back on. That's completely correct. And what all that button is to do is to make sure that these light bulbs aren't broken. All right. That's to make sure that, as light bulbs do, they go out. You don't want to have to be chasing an imaginary ground when all you had is just a light bulb that was out, just went out, and you only had to do is change the light bulb. So you remove the ground, you remove the back feeding of electricity. These light bulbs will go dimmer, this one right here and this one right here. All right. And this one will go back on. All right, and that's the same thing for each one of these light bulbs and any point that we have a ground. So last but not least, and this is the last thing, I appreciate if you guys just stay for the last, like another minute. This is where it gets bad. All right, if you have two grounds on two different wires, this is when you can actually have a problem. Because remember, like I said, this ground right here and this ground right here, you might as well have a damn wire connecting both of them. Take a jumper out and put them together. All right, that's really what you're showing. And not only do you have, just might as well put a wire connecting the two of them, it's going through your hull of your ship. All right, so that's when you can have a problem, and that will pop your breakers. So like I said, grounds are not really that much of a problem. When it becomes a problem is when you have more than one ground. And it's not like this is a lead lag scenario with air compressors. You don't choose when you have grounds. This isn't a normal operating condition. So you have to go chase these. You have to go make sure that you have taken care of all of your grounds. All right, so that way, in case you get another one, which you will, sorry, I just want to make sure I include something for next lesson. So you want to make sure you're taken care of. All right, one ground isn't the problem. It's when you have two of them that you're going to physically start to have problems. And this might be, these motors right here might be your air conditioning. You're going to have a pissed off captain if you have your air conditioning blow because you were too lazy to find a ground. All right. So, like I said, I have a couple YouTube videos that you guys should watch. One represents these ground indication lights. Like I said, he's going to talk about Y and delta. Ignore those from now. It's fine to listen, and if you want to look it up on yourself and learn about it, that's good. But that's going to be your second class cruise where you're going to learn more about it. And then the other indication is how more or less of electricity works in a three-phase scenario where you have three live wires. All right. He does bring up that there's a ground because he is talking residential, but at the end of the day, it still gives you guys a good overview of what's happening. All right. That's the day's class. So if you have, let's see. So we have a quiz on Monday. It's going to be quiz 3. Same way we did it today. Log in. You have 15 minutes to do it. Please log in as quick as possible because today we only had about 45 minutes instead of, half an hour to go over today's lesson instead of 45 minutes. All right, so please get on as soon as you can. If anybody's having any issues with, they're not understanding the material, they're not getting good notes for this, please come see me in my office hours. All right, we can talk through and make sure you have plenty of good notes for all of your tests and everything like that. All right, if you need additional resources, I'm sitting at my computer for 8 hours. I literally just sit there. All right, so come to the office hours if you need it. All right. Otherwise, keep doing what you guys are doing. That was really good on the quiz today. I'm happy about that. So good job.
You wouldn't happen to know about Cruise, would you?
Oh, do I know? I'm just keeping a secret from you guys. No, I have no idea.
I heard that the Parents Association said that it's canceled.
They said it's canceled.
At least that's what I'm hearing.
They don't really, they have influence, but they don't have power. Really what it's going to come down to, like any ship, I would imagine, is the captain probably at his discretion. Now, with that, he's going to have a lot of different things that he knows about, but as you are learning, captain has full safety of the crew in mind, and it comes down to it, even if something bad happens in the engine room, it's his fault. So, all right.
So
Say again?
Oh, for the final, is it going to be like the same questions we've been having, or are you making it like how we've been taking our tests?
I'm gonna have to play around with how we're gonna be doing the final because I have a couple different ideas that I'm throwing around in my own head and how to deal with it. But the problem is that Blackboard isn't very nice with doing pictures. So unfortunately, engineering is a lot of visual. All right, so I'll have to kind of take a look at what we're going to do.
Sure.
All right. Anybody else have any questions? Are you guys all good?
So the grounds that happen on the wires, and you're saying how the multiple grounds leads to like an actual big problem because it connects the wires pretty much. How would something like that happen? Like having the wires get grounded, would it just be like the insulation just rips, like tears a bit and just grounds
Yeah.
itself, or?
That's pretty much it. Or if you have like a bulb where you can actually have, you can have problems with your bulbs that can damage and they can melt and stuff like that. Especially with ships, you have a very moist environment, just because of the atmosphere that's in the engine room, where these ships travel. You can have problems in your motor. Remember, motors are going to be very motors are just pretty much bare copper wire in there, and they can have a ground in there. They can make contact. All these other things, shoddy electricians just going around messing with things. But a lot of it comes down to just old wiring that frays. A lot of stuff's just behind walls, gets painted over, dries out. So, all right. So it just happens. It's not something that you want to happen, but it does happen. But it is from basically wires fraying or rubber drying out and rotting.
So when they're checking the ship and stuff, how do I like check the electrical systems?
So there's a couple different ways you can go about it. We're going to talk about chasing grounds and how you find them in this next class. But basically how to check. So let me write that down so I make sure everyone else gets that.
Because like if something's frayed, like how do we like
How do you,
find
all right.
like if it's in the wall or something?
So basically, like when you go through and you're actually out on commercial ships, you have something called PMs, which are preventative maintenance. Some ships will have electricians that will do this side of it. Sometimes you won't. It all depends on where you go out. But it's say that you should know how to do it because you are the third. Basically, you go through, and there's these devices. And what these devices will do is you connect one lead to the ground or the ground of the motor. All right, so just a piece of the casing of the ship, and then you take another lead and you attach it to one of the leads of the motor, and you basically what's called meg it. All right, and you're sending an electric current through the probe going into one of the line voltages. All right, so it'd be like line 1, line 2, line 3. All right, and those you're looking to see a high resistance because you don't want to see one of the coils of the motor basically send electricity back through the ground of the hull of the ship. That's one way of checking. So you would do like almost like quarterly checks. All right, so like every quarter you would go through and do a bank of motors. The next quarter you do another bank of motors. All right, and you go through that. That's how you would check for grounds and motors. But in wiring, sometimes it's just you got to wait for it to happen. A big thing is that a lot of people are realizing nowadays is that you shouldn't paint wires. Like a lot of people, I don't like it when people paint bolts. That drives me up a wall because of what it does to them. It destroys them. People who paint wires, you don't let the wires breathe, and all the rubber will actually deteriorate underneath, and it'll crack and dry out, and that's when you have a short and you have a ground there. But chasing grounds is a different thing. Sometimes you have to just wait for it to happen. Others, it's just preventative maintenance where you have to go through and make sure that things are done correctly. Going to fuse boxes and blowing out all the dirt, dust, and grime. Hair can catch two different wires and create a short. And if enough dust goes onto a wire, it will create a short. That's really what you're trying to look at. And a lot of things just have PMs that you just go around with an air cannon blowing out certain things, or taking a foxtail and brushing out electrical components. All right. Anybody else have any questions, or is everybody else just staying in?
Have a good weekend.
Have a good weekend. I'll see you guys on Monday then.
Hey, Professor Callahan.
What's going on?
So like me and my buddy, like we found our friend's dad's old dirt bike, and we were like thinking about like fixing it and putting it together. And I was
Okay.
like if you ever did anything like that.
Like fixing an old dirt bike and putting it back together.
Yeah, just like doing anything like that. Just like fixing like old like cars, like mechanic kind of things, or like anything in like that kind of area.
I mean, I worked on my old car that I had, but I mean, it's just, I never went full completion, say it that way. My aunt had an old, the Yamaha Jogs.
Okay.
So she had one of those, and I was fiddling around with it. But then she gave it away to the person who was building her house. So I still have the carburetor for it, like the brand new one I bought. But
Jeez.
a lot of it is just kind of like just diagnosing, just going through it. It's fun though.
Yeah.
Into a project like that.
Yeah, that's what we were thinking. Cause like I was thinking if like we don't go on like cruise this summer, I'm gonna want like a little project on my hands. So I'm like kill the time and stay busy, you know?
Yep. I know how that feels. I have a boat trailer that I rebuilt myself.
Nice.
That's my house.
That's awesome.
So all the electrical, the axles, everything was rebuilt by me.
Good job. That's
There was
sweet.
one bolt holding the entire axle on. You find like you get into sketchy projects like that. You find some really scary things, and it's like, wow, I drove the thing on the highway with one bolt holding the axle on.
That's so funny.
So it's fun though. It's good when you dig into projects. You really learn a lot when you put your hands on things like that.
Yeah, that's what I was thinking. You know, I was like trying to find something to like apply like what we've been like learning in this class. 'Cause, like that's how I feel like things like stick in like my head. Like I actually like learn. Like I'm actually like, putting it towards something. You know.
That's you're not alone on that. That's pretty much the entire maritime community with our maritime college. Everybody I know who acts like that, I got to put my hands on it for me to learn it.
Mm-hmm.
Certain chiefs I used to sail with were like, oh, let me show you how to do it. And I'm like, no, tell me how to do it. So I got to put my hands on it. Otherwise I won't learn. I won't remember. So,
Yeah.
But that's what you got to do. Get a little project for yourself. I don't know if you have like a socket set, but just to get, I have a Craftsman set that's been lasting me forever.
Mm-hmm.
Those mechanics set that just comes with standard everything that you would need to pull apart. The only thing I would add to that is a solid torque wrench.
Mm-hmm.
They're not too expensive. I think they're like $20 on Amazon or something like that, but get a good mechanical one that clicks, not the electric ones.
Okay.
But and then the other thing I would pick up is a like the mechanic sets that like comes from Craftsman. Unfortunately, they don't come with a lot of extensions. They don't come with a lot of swivels and stuff like that. They come with all the sockets you need, but the extensions are where you really need certain things. Motorbikes, mopeds, stuff like that, everything's exposed. But if you're going to get into your car and stuff, it becomes a problem. And I think it's like $20 if you buy the big 20 multi-pack. And then this one time I bought a 3/4 swivel because I was 5 out of 6 spark plugs in on my Jeep, and then I didn't realize I didn't have a swivel to take the last one out. So, I spent $40. 20 of it was on one swivel.
That's all good to know.
Yeah.
Relay that information to my friend.
That and get yourself a good oil like container. So that way, like when you're, changing all the fluids, which is something I would always suggest, is change all your fluids first things. You learn a lot just by doing that. Get a good oil drum that will just hold all of those things. So get it bigger. Don't go for something that's like, only a quart large. Or the first time I ever did an oil change on my my lawnmower was with a plastic bag, and that was awful. Get a good plastic container that you can carry or, move around and dump contaminants into is always a good thing to do.
Yeah, for sure. And so you do office hours tomorrow, right?
Yes. So I'll be doing office hours Tuesdays and Thursdays, 9 to 12, and then 1 to 3. And if those hours don't work, email me. I'm here anyway. We're all under quarantine.
Yeah, sorry. Thanks for everything. I actually really like this this topic right now, electricity.
Yeah, it's interesting. Especially with the fact that shipboard electricity has no ground, which is the really interesting part of it.
Mm-hmm.
I would suggest, like I said, if you're enjoying it, keep trying to learn. Find the spots that you learn a lot, you like, and just learn it.
Definitely.
Like I said, that Ugly's guide to electrical reference is really good. They actually have house and electrical and wiring. Tell you everything you need to know with that.
Engineering Mindset with the guy with the British accent on YouTube. He's got like an electricity like playlist and like his YouTube channel, and it's like awesome.
Yep, that's one of the videos I'm about to post to everybody. So he has all of that. Yeah,
you posted. That's where I found it. You posted that on Blackboard.
Mm-hmm.
So I just watched the one you posted, and I saw he had like a whole like playlist of things. So I was just like running through those. Like that was like really informative.
Oh yeah, there's a lot of good stuff out there on YouTube of engineering. So if you're ever confused on any of that, or if there's anything like when I learned all about, I think we're going to get into motors, but we'll definitely have the time. But basically, there's different types of motors out there. They have like squirrel cage, they have induction, they have all these different types. And the big thing on YouTube is that helped me with my license is that if you go through and do, like I just typed in squirrel cage animation and type in motor, because otherwise you get some weird things. But you type that into YouTube and you get these really great let's see. You get these great animations. And that goes for basically all, I don't want to add that to a queue. My internet has just went to nothingness these past days.
Yeah, everyone's been on it 24/7.
Yeah. But here's an induction motor. If you look up in this top right corner, they basically go through and they have a full animation where they did like SolidWorks. There we go. And they go through and explain the whole. It's usually some Indian guy. And they basically pull apart the entire motor. And unfortunately, some things like this just can't be done in class, where our limitations are with this. But they go through on how it all works in certain instances. And this guy's Learn Engineering. They're fantastic.
Yeah.
So, typing into that will get a lot of information for you too.
Yeah, you can always trust an Indian guy when he's teaching engineering.
Yeah. Or some crazy, here's how I wired my house with, that wasn't code, but it works. But, all right. But yeah, I have office hours. If you need them, come to them. Go through anything. Say again?
I'll definitely check those out tomorrow for sure. You said 9 to 11, right? 9 to 12. And then, so let's see, 9, 10, 11, 12. Yep. All right. And then from 1 to 3. That's the same for Tuesday, right? Yes. And then you just go into there's an email that I sent out that has the link, and then also there's Blackboard has the link, just says office hours. Okay. All right. It doesn't just have to be the office, it doesn't just have to be what we're doing in class. If you're confused on anything else too with class that we've done.
All right.
All right. Thank you. Appreciate it.
Yep. Anytime.
All right. I'll see you tomorrow.
See you tomorrow.